Okay, so thank you very much for the invitation, and happy birthday to Eugene and Rayer. This is a talk about symplectic topology, not really in the same direction as a lot of the other talks in the conference. I feel a little bit like the gym teacher at a high school where the students were happy learning about dolphins and Shakespeare, and then tells the students that they have to climb a rope to the ceiling, but I hope that you appreciate the rest of the conference more, because once it's over, you can go back to what you were happy learning about. Okay, so what's the setup? So the setup is that I assume I have a contact manifold, which is a circle bundle, over some symplectic y. So alpha will be the connection 1 form, and the omega in the yeah. Is symplectic form on y is minus d alpha on the contact manifold. So alpha is the contact form, and so then I have a Lagrangian in y, and I assume this has a horizontal lift. In Z, which is a Lagrangian. By definition. And so one kind of question you can ask about this is how many exact or not exact fillings of this pair, Z lambda, are there up to various kinds of equivalence relations. And so an example, this is going to be a finite to one. Map, and so what's an example? Well, I can take the n-1 torus in the unit sphere. So this is the set of n tuples of complex numbers, so that each norm square is 1 over n, and the phase is fixed by requiring that, or the product is fixed by requiring that the product is real. Okay, so so this is a subset of the unit sphere in the complex n space, which is my contact manifold, and then this projects onto CPn-1 with circle fibers. So what's the claim about this example? Well, what one claim is that there are no exact fillings, at least if, well, what's a filling? The fillings will be called XL. And so you have to choose an ambient symplectic manifold which fills the contact manifold, and then you have to choose a Lagrangian filling of the Legendrian. Yeah. 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 So this is.
Oh, sad. Oh, I'm sorry. I'm
yeah.
sorry. Sad. So the total space is the sphere.
Yeah.
Lambda.
Yeah.
Yeah.
So if this maps by the moment map to the n-1 simplex, and then the pi will be the Lagrangian torus orbit right in the middle, and then I'm taking the whole. Yeah, really the inverse of the pre-quantum bundle, and then taking the horizontal lift of that. And because you can multiply all these complex numbers by an nth root of unity and still satisfy the equation, it's n to 1 over this is called the Clifford torus. Okay, so at least if X is just the standard unit ball in CN, then there are no exact fillings, and there's one non-exact filling, and that's the only one up to an equivalence relation that I'm going to describe. But there are, even in this simple setup, there are a lot of other. This could be example A. And then B, I could just take the same n-1 torus, but I could multiply by some phase which doesn't preserve the equation, that the product of the coordinates is real. So I need a 2n here. Let's see. 2n. So I could do something like this. And so then the claim is that now there is an exact filling. And the number of fillings up to equivalence is 2. Okay. Yeah, it's a little. I'm being a little vague about what I mean by filling. So an example that I want you to think of, maybe for the purposes of this talk, is just the unit ball. Yeah, but you could also have infinite fillings, in which you have a Lagrangian which is asymptotic to a Legendrian at infinity. And you get slightly different answers depending on which notion of filling you consider. But for the purposes of this talk, it's not going to matter. You can think of it either way. Yeah.
So your filling is a symplectic manifold with the unit ball onto n.
Yeah.
Its boundary is a contact manifold.
Yes.
It's a circle bundle.
Yes.
But you also want to look at something whose boundary is your Lagrangian.
Yes.
So
that should be the Lagrangian filling. Yeah.
And will it be the same thing? We just allow small norms.
Yeah. So let me write down what the two fillings are in this case. Okay. So if I just want the filling of Tn-1, then I can take L to be the set of Z1 up through Zn in Cn, so that Z1 squared, Zn minus 2 squared, and all of these norms are equivalent up to some constant, which is only applied to the first n minus 2 coordinates. And then I fix the phase to be in 0, infinity. Okay, and so that this filling was introduced by Harvey Lawson. And it's asymptotic to the torus that I wrote up there. If I would cut it off at finite distance, say by intersecting with a unit ball, then you would see the appearance of these constants. But you can get around that by sort of deforming things a little bit. Well, deforming the lambda a little bit. So, and small deformations like that aren't going to affect anything in this talk. Yeah.
I'm sorry.
Yeah.
I don't see the e to the pi I over 2n as an element. It's supposed to be a filling for c, right? But I don't see where the e to the, I don't see where the switching factor is coming in.
Oh, this is just a filling of the first factor.
Okay.
Yeah.
Okay. Sorry,
So if you wanted a filling of this union, then you would double this by taking this thing and multiplying by a phase. Yeah. So the double filling would be this plus its phase, and so then you would get, two things that look like this. So the Tn minus 1 here, and then the e to the pi I over 2n Tn minus 1 would be this one. But there's another filling which L prime, I can take Z1 up through Zn in Cn, and now I can require that the product lies in R plus I epsilon. And all of the norms are equal. And so then I get a filling which connects the two like this. So this filling here, this is isomorphic to a Tn minus 2 times R2. This filling is a Tn minus 1 times R. And the claim is that up to some kind of equivalence, these are the only two fillings of that disconnected Lagrangian. Okay. I'm not really sure what happens if you allow other ambient symplectic manifolds. The results we have some technical restrictions on the type of filling. So even in these simple examples, I don't really feel I understand the whole answer. Yeah. Yeah.
So are you letting? So I guess you're working with a ball, not with cement, right?
Yeah. So if you would truncate it at the ball, then you would have to throw the epsilons into the definition of the torus, and so that would give you a filling of a slightly deformed torus.
So this is a filling of a deformed torus. I'm just trying to understand.
Yeah. This is a filling of the deformed torus if you cut it off at finite distance. But then if you think of it as
But then it's too big. Or you think you compute
yeah. In the end, the symplectic form isn't going to matter. Yeah. Yeah. Okay. So let me.
So this is for a fixed epsilon. Are you varying epsilon?
No. Epsilon is fixed. So let me correct. Filling of Tn minus 1 perturbed by epsilon. Yeah. Yeah, there's sort of a toric picture. So if you think about the moment polytope of Cn just as a orthant, right? So then you can either think of the simplex at finite distance or at infinity. And then you're taking something here, and you're trying to go to 0. If you would just take the cone, then you would just go to 0, right? But if you shift it a little bit, then you sort of L is sort of this thing, and then it becomes smooth. Yeah. Okay. Okay. Yeah. Thank you. Any other questions? Yeah. Pictures is worth 1,000 equations. Okay. Okay, so let me talk about the motivation for this. So the motivation comes from mirror symmetry. So in mirror symmetry, if I have a symplectic manifold Y, it's supposed to be mirror to some complex manifold. Or space with some potential W. So in the Calabi-Yau case, which is the case that most people focus on, this potential is just 0, and you just get a mere complex manifold. In these Fano examples, what I'm talking about here, like complex projective space, the mirror is equipped with some function. But I don't really want to worry about this distinction too much. In particular, if I have a Lagrangian L, then its mirror is supposed to be something like a sheaf. I mean, actually, in the Fano setting, it's a matrix factorization of sheaves. But anyway, it doesn't matter. The point is that you expect a deformation space with good properties. E.g., something like a complex structure with finitely many components. And def here is a space of deformations of L. And this is supposed to include the case when L is singular. And in particular, when L is just something like the cone on some Legendrian lambda. One expects a good deformation space. And it's natural maybe to, can people see over here? It's natural maybe to think in the talks that we've had earlier in the conference, whether you can define a deformation space like this just using, say, rings, some sort of ring spaces, and then maybe look at families of ring spaces and so on. But as far as I know, I don't see a way to do that. I mean, the approach that I'm going to talk about is all about using holomorphic curves to define this deformation space. Okay. So the goal is to try and describe what's called the augmentation variety of lambda, which is morally a version of the deformation space of the cone of the Legendrian. Okay, so Okay, any other questions before I keep going? Okay. So,
Question.
yeah.
So fixing the Lagrangian at infinity,
Yeah.
is that analogous to like fixing the Hilbert polynomial of the sheaf or something?
It's usually thought of as fixing the support of the sheaf, some sort of micro support. Yeah. Okay, so I want to talk about contact homology of Lagrangians in its treed version. Okay, so to define contact homology for Lagrangians, we start off by looking at the red chords. So these are paths in Z, which are lying in the fibers in our case, and for which the gamma dot of alpha we can normalize to be 1. And then we look at words in the red chords. And then we take the space of chains to be a copy of the coefficient ring for every word in those red chords. And the standard choice of coefficient ring is to do, you take the first homology of the Legendre, and then you make that, you take the group, you make that into an algebra. And isn't it an honest monoid? I have to think about why is it just a pre-monoid?
Are there relations?
No.
Free, he said, or now free.
Oh, free, yeah, right, yeah. Thank you. Okay, and then there's supposed to be a differential on this delta, which counts J holomorphic maps to the symplectization bounding. Oh, yeah, thank you. Yeah. Thank you. Bounding the R times lambda with a single input on each component. So the picture looks like this. So I'm going to if I want to know what happens to any particular Rabe chord gamma, then I look at the number of holomorphic curves in R times Z. And I try and weight this by the boundary of the holomorphic map. And you'll notice that the boundary is not really a loop, right? It's it's a loop up to the fact that you have to insert the RAID chords. But the standard thing to do is to choose some sort of caps here. Like you choose a base point, and then I would connect the two endpoints of the RAID chord to the base point, and then that would give me a first homology class. Although, of course, you know, there are going to be different choices, so it's going to break symmetry in general when you do that. Okay, so in the standard version of this, what you do is you want to get something which is at least countably generated. So if I take a generic contact structure and I take Y to be exact, then this is the version that was studied by Ekholm, Etnayer, Ng and Sullivan. And a paper that we found inspiring was by Dimitrikou Rizal. I can't remember whether it was 1Z maybe, and Golovko. Okay, this is a short hyphen because it's one person, and this is a long hyphen because it's the second author. Okay, so then anyway, then you have countably many RAID chords, and then this you can at least try and set this up so that del squared is 0. But I want to talk about a treed version, which is called the Moore-Spot case. So I don't want to take a generic contact structure. So why is it called Moore-Spot? Well, it's like in Morse theory if you choose a function which doesn't have isolated critical points, and then you have to come up with a different way of defining the complex. So we choose a Morse function from the space of RAID chords disjoint union, the Legendrian to R. And then we get a vector field which is just, it's the gradient vector field with respect to some metric on the first factor. And on the second factor, it's some translational thing plus the gradient vector field here. So this is actually similar to what you would do if you do Morse theory with boundary. There's a theory of Morse homology with boundary where you assume the function is tangent, the gradient flow is tangent to the boundary. And then if you viewed that boundary as a cylindrical end, then you would get this kind of vector field there. Okay, so then anyway, instead of this picture, so then you get pictures, yeah.
How should I think of this one to
Yeah, it'll become clear in just a second. Yeah, let me draw the picture. So the problem is if I don't take a generic context structure, then there are infinitely many possibilities here. But then I require that at each end, there's one of these gradient flow lines of the, well, in my situation, the Z is just a circle bundle, right? So each of these RAID chords, the intersection of lambda with any fiber. Yeah.
That is your contact length.
Yeah.
On the given
Yes.
That's just that red chord is, you're saying, just
Fibers.
that's pieces of fibers that sort of
Yeah.
that start and end in your
Yes.
lambda. Lambda was
Yes. Finite to 1 over the base.
but transverse to the circle fibers.
Right.
Transverse to the circle fibers.
Yes.
That is the
Right. Yeah, so a typical picture of a RAID chord would be either something like this.
So what you're saying is in this example, we actually have an actual.
Yeah, the R lambdas are infinitely many copies of lambda, where you have to specify the beginning point of the RAID chord and then also what angle you go around. Yeah.
So what's this disjunctive?
Well, because I need to allow not only
So R lambda is a manifold, finite dimensional.
yeah. Yeah, in a second, I'm going to allow situations where you have disk bubbling. Maybe this is a good point to sort of say what the sketch of proof of the d squared equals 0 relation is. So the proof of the del squared equals 0 relation is supposed to be that if I have some contribution to del squared, it looks something like this. Okay. So each one of these is a contribution to del. I said what happens if you have a single input. If you have multiple inputs, like in this case, you just use the Leibniz rule. So this picture here represents a holomorphic curve with one input, but then I extend it to something acting on multiple inputs by just letting it act trivially on the other inputs. And so this two pictures glue together and give you a contribution to del squared. And so this kind of configuration is the boundary of a one-dimensional moduli space of such curves. And if this is the only kind of boundary configuration, then the boundary terms occur in pairs and cancel. And so then you would get d squared equals 0. So if this is the only type, good. Yes. 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 Right. So the input word here would be, say I have one word here, one output word here. At each stage, I only consider non-trivial holomorphic curves acting on one of the inputs. So all of these other things are just trivial curves in R times Z.
I think I'm confused on how to think of the word, because you draw the picture and I'm sort of seeing, see a two-dimensional thing that you're trying, and I think, okay, the boundary keeps in circles.
Well, this is a rib chord, right?
Yeah, but you have words and chords.
So the word would be gamma 1, gamma 2. No.
So you actually care about the ordering.
Yeah, you care about the ordering.
In this picture, the sort of three inputs or outputs, and
Yeah.
what they are.
The convention is to go this way. Yeah.
In that picture, you have an actual curve.
Yeah.
That actually goes in this abstract thingy and goes to the vector.
Yeah, it has the asymptotic limits. It has asymptotics.
So should we think about this as a complex dimension with boundary,
Yes.
but the boundary is corners?
It depends whether you compactify or not.
Like the.
So if I compactify here and here, I would get corners.
Up and down, are you getting a boundary, or is this sort of? The chords are close.
Let me, I think I was about to give an actual example. Right. Yeah, let me do, okay, so your first answer was why your first question was why do I need these things here?
No, I'm just trying to say.
But let me finish that answer. And then I'll answer your other question. So in a second, I'm going to allow situations with bubbling. And this is going to mess up the d squared equals 0 relation because it's another codimension 1 boundary. But what's going to happen here is that these things are going to, I can have configurations which are connected by gradient trajectories. Okay, but let me come back to your other question. So let me just write down an example. So example. So let lambda just be S1, sitting inside Z, which is S3. And now, if I take the symplectization of R times Z, I'm just adding in the radial coordinate. So this is the same as C2 minus the origin. And if I take R times lambda, well, S1 here means the Lagrangian I had before. So what were my conditions before? I required all of the norms of these to be equal and equal to 1 over n. But now I'm taking the product with R. So now the total norm is not going to be fixed. It's just Z1 norm equals Z2 norm. And Z1 times Z2 was supposed to be real. Do I want real positive or real? I think maybe there was a mistake before. Yeah. Yeah, I should have had R plus before. I'm sorry. Yeah. Yeah, the first one I want it to be, yeah, n to 1 over the connected thing. So yeah, I forgot the R plus. Okay. Not everywhere. Yeah, I think I left out an R plus a couple of times. So let's see. Okay, so I want curves bounding this Lagrangian now. So let me take my domain to be the upper half space. I think of this as a holomorphic curve with one strip like n at infinity. So the boundary of H is this thing here. And so now I just write down what the maps are. So I want to map to C squared minus 0. So it's going to have 2 components. So I could take something like Z Z minus I or Z plus I, something like that. And then I want to stick in something over here so that when I take the product, I get something real. So this could be Z plus I, or if I take the other choice, Z minus I. Okay. And it's not hard to see. Those are the only 2 maps with this particular domain. Say it again. No, because I only want the boundary conditions to hold when z is real, right? I don't care what the condition is when z is not real. So when z is real, z is equal to z bar, so I don't need it. If I would put a z bar there, and it also wouldn't be J holomorphic for the standard structure. Yeah. Okay. And again, since this is a toric conference, what's the toric picture? Well, y in this case is just a CP1, right? And so I have these two disks in CP1, the left and the right hemisphere. And R times Z is now a C star bundle over CP1. So these are just the two lifts, depending on the sign, of the two hemispheres. And that's what sort of makes the toric case particularly nice, is that the disks in the toric variety are more or less known by Blaschke and Cho-Oh, and you can get a lot of partial information just by writing down holomorphic disks in the toric variety and lifting them. Okay. So at infinity, this holomorphic map is asymptotic to some Rabe chord. So that Rabe chord now, in the differential, it has one input because my inputs are on the right, and it has no outputs because there's no outgoing Rabe chord. But that doesn't mean that the differential is zero. It just means that it's a multiple of the empty word coming out. And in order to do the computation correctly, you have to make this choice of capping path here. So you have to decide how to close this up into a loop. And you also have to make a choice of spin structure. With the standard choice, you get something like this, where this is the generator of H1 of lambda, which is Z. Okay. So that would be the version where you don't consider this extra stuff coming from trees. If you include the extra stuff coming from trees, you get 1 minus mu e to the x, or x is the degree 0, degree 1, excuse me, critical point on lambda. So this tree stuff means you have additional contributions from spiky disks that look like that. Okay, so did that at least give you some idea of how the...
One thing I read from the picture is that if we go up, it's closing up, I was just trying to understand the picture.
Okay, so the inside of the curve is mapping to, in this case, c squared minus 0.
No, I'm just saying, like, on the right-hand side is the circle, it's not an interval. I'm asking a very nice question.
Oh, this thing here.
It's a circle, not an interval.
No, it's an interval.
It is an interval.
Yeah, it's a Rabe chord.
So, but you're mapping, again, the domain of your thing is where's the boundary of oh, that's the boundary of left half plane.
Yes.
The whole thing is the boundary of
Yes.
not the.
Yeah, so if I draw it in this picture, then the asymptotic limit would be some Rabe chord.
So this is
Yeah.
not like another boundary system exponent, but rather it's asymptotic.
We think of it as asymptotics. You can also compactify. And if you compactify, then there would be an actual limit. Then the domain would be a manifold with corners, exactly. Yeah. Yeah, but it's better to think of it as an asymptotic. Okay, so the claim is that d squared equals 0, and if you take this thing, then this is satisfies some TQ of T axiom for at least some class of cobordisms. So if I have a symplectic manifold with two components of the boundary that I've decided are the incoming and outgoing contact manifolds, then I can assume that my lambda minus and lambda plus extend to some.
So here, should we be thinking of the contact as a constructive bundle, or is this?
Yes, yeah. This is for the assumptions that I wrote before. Yeah. Or in low dimensions, or in this exact setting that Etnayer, Eckham, Ing, Sullivan wrote. There's,
Is the
yeah.
goal to try to produce invariants of Lagrangians inside these two prediction bundles, or getting more structure? What is the?
Yeah, so the idea is to produce obstructions to fillings and a notion of equivalence on fillings so that you can classify things up to this equivalence. Right. So the focus is really not on the homology itself, although that's interesting. But in particular, if I have a cap-free filling, XL of Z lambda, then this gives an augmentation. So an augmentation is a chain map from the Chekhov-Eli-Eshberg complex to, well, if you have a filling, then the output Legendrian is empty. And for an empty Legendrian, you only have the empty word because there are no Rabe chords. So this is just the trivial complex. Now, at least after tensoring, you have to tensor with group ring on H1 of L because now you're going to count curves in X comma L, not in R times Z anymore. So I only have when was I supposed to stop? At 10. Okay, I have a minute. Yeah. So. So you have fillings are supposed to give you, at least in good case, augmentation. So by studying the augmentations, you can say something about what fillings there are. So the augmentation ideal is, I just take all augmentations. I look at which elements of the Chekhov-Eli-Eshberg algebra it kills, and then I only look at those elements in the Chekhov-Eli-Eshberg algebra, which are polynomials in the mu I e to the xi. So these were generators of H1, and these were things in the degree 1 things on lambda. Anyway, so you think of these as coordinates on the representation, abelian representation ring of lambda. So they define an augmentation variety inside the space of homomorphisms from pi 1 of lambda to C star. Okay, so this is called the augmentation variety. And so the example would be again, if lambda is T2 sitting inside S5, well, now this projects onto CP2. So I think of my Legendrian as living over the center of the moment polytope, and then there are these 3 disks. And these lift to curves in the symplectization of Z, and you get this formula that the boundary of this has 3 terms given by these three disks. And if I have an augmentation, then it's a chain map. And in this trivial complex C of the empty set, the differential is 0. So this tells you right away that the augmentation variety of lambda is contained in this locus. But now you have the existence of a filling. The Harvey-Lawson filling. And it doesn't matter here if I perturb a little bit. These epsilons don't matter when I do holomorphic curves, because the spaces of holomorphic curves are invariant under perturbation once you cut them out transversely. So this implies that the augmentation variety is non-empty, because I have at least one. But then this is an irreducible polynomial. So you get equality here. So what Dimitroglou, Rizal, and Golovko conjectured is that a similar thing happens for any toric variety. That you can describe the augmentation variety of the toric Legendrian in terms of the moment polytope, with basically one contribution from each facet of the polytope. And we've proved at least part of that conjecture. It's not really clear how much of it we've proved, but at least some more cases that are new. Okay, so I'm over time. Thank you.